We are now going to move on to a new topic known as photoelectric effect. It was observed that many metals emit electrons when a light shines on their surface, and this is known as the photoelectric effect. Okay, let's see what this actually, or the setup of what this looks like. Okay, so you have this evacuated chamber here, and you have a metal surface. So they looked at different metals. They looked at sodium, magnesium, and so forth. But this metal was composed of only one thing. So let's say sodium. Okay, then they shined light on this metal surface, and what they noticed were electrons would be emitted from it. The reason why they knew electrons were being emitted is that it would travel through this wire and connect with this battery, and it would produce some amount of current. So they knew that electrons were being emitted due to the current being measured from it. Okay, now on the left side, figure A, this is just showing a really close-up view of the electrons. So you have an electron sitting on the surface of a metal. It's attached to an atom, right? So when there was light, when it hit that electron, the electron got excited. So if it got excited, it has a ton of energy, has so much energy it doesn't even know what to do with it. So it gets emitted from the atom. It just has so much energy that it gets removed from the atom. And then that electron then goes to the rod, and then we can find the current associated with that. Let's view this photoelectric effect a little bit more because it's very, very interesting. Classic wave theory attributed this photoelectric effect to the light energy being transferred to the electron. Let's look at a few examples here. So, according to the classic wave theory, it says if a wavelength of light is short, meaning high frequency, so if we have a short wavelength, this would be an example of purple light. So let's just draw an example of that. Purple light frequency, very, very fast. And now it hits a metal surface. More electrons are being ejected. So you get a ton of electrons being ejected. Let's say you do the opposite way. Instead, let's say you have a wavelength that is very low energy. Low energy would be an example of a red light. So if it has low energy, you're going to have a long wavelength. Okay, so long wavelength, and it hits a metal surface. According to this, you would get some electrons being ejected, but not as many. So you would get like maybe one electron. But if you use very high light, for example, or very high frequency, such as that purple light, you would get a ton of electrons. Okay, now that is one way we could look at it. The other way that classic wave theory said is if the intensity is brighter, so that means you have a bigger amplitude, more electrons are being ejected. Okay, so let's say you have a wavelength. Let's say you have a very large wavelength, or large amplitude. So very, very large amplitude. It hits a metal surface. You get a lot of electrons being ejected. Okay, and then because I'm kind of running out of room, I'm going to do another example over on this side. Let's say we have the same wavelength but a very low amplitude. This would make it very dim. If we have a very high amplitude, this would be a very bright source. Okay, so a very dim light, same wavelength, but the amplitude is shorter. It hits a metal surface. What would happen? Okay, Okay, so according to this, what would happen if you use a dim light? What do you think? According to the classic wave theory, here is what they predicted. They said with a lower amplitude, so a lower amplitude, this means you have a dim light. There would be a lag time before electrons are emitted. The reason for this, they said, was that the electrons would have enough time to absorb energy. So, as a review, with a dim light, they said with a lower amplitude, there would be a lag time before electrons are emitted. The reason for this, they said, was that the electrons needed enough time to absorb energy. Okay, so looking at our example here, the electrons would have to get enough energy, and then once they got enough energy, then oof, they could move, right? They could be emitted. But this was not the case. So something is going on. And Einstein is the guy who looked at this effect, this photoelectric effect. Let's delve deeper into what is going on with this. So experimentally, they used sodium, and they had light hitting sodium, and electrons were being ejected, right? So you have light coming in, it hits the sodium metal, and then you have the electrons being ejected. Now, with blue light, this has a very high energy. The electrons are going to be emitted. So blue light, very, very high energy. That means the frequency is going to be high, the wavelengths are going to be short, and hits the metal, and electrons are being emitted. So you get a lot of them being emitted. Now this occurred even with a dim blue light. Okay, so that means with a dim one, it's not going to be as bright anymore, but you still have the same wavelength. It's just not going to be as tall. So when it hits the metal surface, you still get the same amount of electrons being ejected. Now with red light, red light has a lower energy associated with it. The electrons were not emitted, even though it occurred with a bright red light. So even with a high amplitude, high intensity, it did not matter. So even with a high amplitude, when it hit the metal surface, nothing happened. So they thought classically that the electrons would have to get enough energy, like they would just have to hold off and they would absorb that energy from that red light, and then once they got enough energy, then they can move. But what they observed was that this was not the case. So even if they used a red light with a high amplitude, no electrons were emitted. Let's think of this as an analogy, because you may be kind of lost right now. Think of it as ping pong balls. So no matter if you throw them slow or fast, and no matter the amount, so if you throw 1 versus 100, you will never be able to break the glass. This would be an example of that red light. So no matter if you use a dim source or a bright source, no electrons would be emitted. Now let's look at a baseball. No matter if you throw them slow or fast, and no matter the amount, you will always break a glass. So no matter if you throw 1 of them or if you throw 100 of them, you'll always break the glass. And no matter if you throw them hard or fast, you're going to break the glass. This would be an example of that blue light. So no matter if it was dim or bright, blue light always had electrons being emitted. Now, a minimum frequency was needed before electrons would be emitted regardless of the intensity, and this is called the threshold frequency. So, for example, let's look at this figure. On the y-axis, you have the rate of electron ejection. On the x-axis, you have the frequency of light. Okay, so they looked at, let's say, red light. Red light has a frequency of, let's say, right here. No matter if it was dim or bright, look how there would be absolutely no electrons being ejected. Okay, and anything below this red light, they also notice nothing would happen. No electrons would be ejected. Okay, but then when they got to this blue light, blue has a higher frequency than red, then electrons would be ejected. Okay, now there's going to be 2 different areas. You can have a high light intensity versus a low light intensity. Higher light intensity, you'll just get more electrons being ejected. With a lower light, you'll still get electrons, but not at the same rate. So high frequency light from a dim source caused electron emission without any lag time. It just happened instantaneously. So from this, Einstein proposed that the light energy was delivered to the atoms in packets, and this was called quanta or photons. This was revolutionary at the time because they said, hey, look, light behaves as a particle. Okay, so on a essay question or something like that, if I asked you about why the photoelectric effect was important, it's because light behaves as a particle. At this time, they thought light was a wave. So they thought light looked something like this. But what they saw was light was kind of like a particle. So it would hit the electrons, and then you could get the electrons being emitted if it had enough energy to do so. So the energy of a photon of light is directly proportional to its frequency, and it's inversely proportional to its wavelength. And we are given these equations where E equals h times nu. H is this Planck's constant, 6.626 times 10 to the negative 34 joules per second. And this nu is our frequency. Now, because nu is equal to c over wavelength, you could also, wavelength, make it look a little bit nicer. You can substitute that into this equation, and you can get E equals h times c divided by wavelength. Both of these are the same thing.